Welcome everybody to today's webinar. It's my great pleasure to today have the completion seminar of Zebedee Nicholls. Let me please join me in acknowledging the traditional owners of the various lands that we are joining this webinar from, and in paying the respect to their elders past, present, and emerging. So today you will hear about the state of reduced complexity climate modeling from Zebedee Nicholls. As I said, PhD completion seminar. He did his PhD in the last years with myself and David Caroli and Peter Rayner and Alexander Nowells as co-supervisors, and there's also Robin Schofield and Todd Lane on the advisory committee. Now, that is a normally, completion seminars are an end of an era. I think Zebedee's PhD was a beginning of an era. But before I come to that, let me tell you briefly a few points about Zebedee. So Zebedee was homegrown here in Melbourne. Then he did a first-class honors in Oxford. There he also, what I just learned, was a triple jump master. He was junior president of the tennis club. And yeah, as a Zebedee choosing me and the others as a supervisor, I felt very, very privileged. And I have no illusions that it's because we are sitting in Melbourne and not because of whatever else we do, but it was really fortunate situation. And normally with a PhD student, you have the feeling by the end of it, the PhD students really overtook their supervisors, etc. But with Zebedee, it was slightly different. It was rather early on he gave a hard time to the supervisor, at least to me, of I had to convince myself that I'm not completely redundant yet. And Zebedee was kind enough to every now and then still ask me a question about climate science, but his programming, which is about a magnitude faster than mine is, his master skills, his grasp of climate science are just unparalleled. And so that's why I say Zebedee's PhD is a beginning of an era, because he put over the last 1.5 years that he worked with me now in the IPCC working group 1, he put so much additional rigor in the machine room of the IPCC to make cross-chapteral statements more consistent. I think he's contributing author now of the forthcoming IPCC report of at least 4 chapters, but there might be more. He, together with our colleague Jared Lewis, he put community data sets out there that are now the go-to place. You find them on cmip6.science.unimelp.edu.au, for example, on the CMIP6 models. And just as a side effect of his PhD, he also managed to build a whole international community on reduced complexity modeling, which was not existed before. And so it's that completion seminar is now, again, not an end to an era. His PhD is really the start of an era of more rigor there and much more scrutiny and much better results in the probabilistic reduced complexity climate modeling, so that they can really inform decision makers with getting multiple lines of evidence together. Yeah, without further ado, I will hand over to Zebedee for a fascinating talk. And at the end, we have opportunity for question and answers. Please, throughout the seminar, use the chat to discuss among yourself also. And if you have any questions that come to your mind, please put them in the Q&A session. And there you can also upvote other people's questions. We don't have that many people today, but so please be active on both chat and Q&A. I hand over to Zebedee.
Thank you, Malta, and thank you for that very warm introduction. It's very kind. I'd like to start by also paying my respects to the traditional owners of the land we're on today, and acknowledge their elders past, present, and emerging, and also that the land I'm on today, at least, was never ceded. So as Malta said, I did my PhD on the state of reduced complexity climate modelling, and Malta was my lead supervisor, and I was extremely privileged to have Malta as my lead supervisor. He's taught me an amazing amount and really given me the freedom and belief in myself to take things a lot further than might have happened otherwise. From my wider supervisor team, I think I might be correct in saying that I am the last one out of the Malta David stable. And I was also supervised by Peter Rayner and Dr. Alexander Naus, who's based at Climate Analytics in Germany. I was lucky enough to have newly Associate Professor Robin Schofield, so congratulations Robin on the promotion, and then Professor Todd Lane rounded out my advisory committee. Before I start, I think there's some thank yous that I need to make. People say it takes a village, and I think for my PhD, it's definitely true. So as we've spoken about, obviously my advisory panel were very important. I want to give a particular thank you to Jared Lewis. So Jared is the software engineer who works with Malta and I, and without him, this PhD project would definitely not have happened. The amount that Jared has taught me on the software side, but also on scientific rigor and how to make all these things work, as well as a number of times that Jared has solved bugs for me that I couldn't, is uncountable, and I'm really indebted to him and all his work. I'd like to thank my partner Sasha for her patience over the last years, and all my friends, family, and my housemates who have put up with me being probably grumpier and more neglectful than I'd like to be at many various times. My international collaborators, so both at the Potsdam Institute for Climate Impact Research, and particularly Katja Frieler, who hosted me, and Robert Giesecke, who taught me an amazing amount during my stay at PIC, and then Piers Forster and Chris Smith at the University of Leeds, who also hosted me. And finally, to all of my Climate and Energy College colleagues and friends, the college is an amazing place to study and really provides a really special community. And I can't thank you all enough for your support throughout the entire PhD. I don't think I would be here without all of you guys. And finally, to everyone in the audience for turning out at 4:30 on a Tuesday afternoon and potentially going till 5:30 or even beyond. It's very nice to know that people are interested enough to make it at this slightly odd time. So, on to what I've actually done in my thesis. Many of you will know this picture. For those of you who don't, this was kind of the celebration at the signing or the agreement of the Paris Agreement, where the world came together to bring in place new targets for tackling anthropogenic climate change. And there were two key clauses in the Paris Agreement, which I want to just read out. So the first is from Article 2, where the countries agreed to take steps towards holding the increase in the global average temperature to well below 2 degrees above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels. And the second one is from Article 4, and that states countries are going to achieve a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of this century. So these are two very important goals in the Paris Agreement, but they don't exactly quantify things like, okay, what does it take to achieve 1.5 or 2 degrees? When exactly in the second half do we need to be at net zero? So fortunately, there's a whole world of scientists which are doing their best to answer these questions. And one such effort was a special report on 1.5 degrees, which was done by the IPCC. And they addressed the question of what it takes to achieve a 1.5 degree temperature goal. And they came up with this statement, which is, in model pathways with no or limited overshoot of 1.5 degrees, global net anthropogenic CO2 emissions declined by about 45% from 2010 levels by 2030, and they reach net zero around 2050. You can see the ranges in there. This is all fairly jargon filled, but basically they've gone and crunched the numbers, and it looks like net zero around 2050 for CO2 is where people should be aiming. And Bloomberg recently did an article where they called this one of the most influential sentences ever written, and they had the slightly hyperbolic title, "The world is moving towards net zero because of a single sentence." Now, I don't think that's quite true, but I think it's had a huge influence, and I think it was a very important assessment. So the question is, well, how was this statement actually derived, and how was the categorization performed? And when you dig through the special report on 1.5, you find it all rests in large part to one particular model. And this is the reduced complexity climate model, Magic 6, which Malta developed and has put a huge amount of work into, and is really one of the key tools in the climate assessment realm. And my project focuses on models of this type, reduced complexity climate models. Magic's a really key example of them, but there are a few more out there, or many more out there, and I tried to spread the net slightly wider. Now, the statement about reaching net zero in order to make 1.5 degrees was obviously based in large part on magic. But if you dig further in the special report on 1.5 degrees, you find this statement, which is that the veracity of these reduced complexity climate models is a substantial knowledge gap in the overall assessment of pathways and their temperature thresholds. And this is the knowledge gap which basically defines my PhD. So on the one hand, you had SR 1.5 making quite strong claims about what was required to meet certain temperature targets. And on the other hand, you had this statement buried in the supplementary material that actually said, well, there's quite a big gap in the literature about how these models behave, and really we should fill this. So that was the major motivation for my project. So today I'm going to go through my project and how it worked based off that motivation. So I'm going to start by just taking a step back into what's called the climate model hierarchy and actually trying to define what we mean by reduced complexity climate models. I'll then go through the project motivation in a bit more detail. And then the next 5 sections are the 5 chapters of my thesis. So they include some CMIP data processing, some evaluation of reduced complexity models, some application and some development. And we'll see how this all fits together in a little minute. And then I'm going to end with conclusions and outlook for next steps. So I could obviously talk for a while on this. I've spent quite a long time thinking about this project. I don't have quite the full amount of time I would like to have today. So I'm going to just focus on 2 chapters in moderate detail, and the rest I'm going to go through pretty quickly. The aim here is to give an overview of the project and how it all pulled together. But if you want details on one chapter in particular, please feel free to reach out to me. So let's just take a look at the climate model hierarchy before we move on, because this can get rather messy. Firstly, there's a whole bunch of acronyms that I'll probably use throughout today, which are worth just quickly going over. So I use RCM to mean reduced complexity model or reduced complexity climate model. EBM is energy balance model, and they're essentially a subclass of reduced complexity climate models, although they do get used in different contexts. I won't use EBM too much. EMIC is Earth System Model of Intermediate Complexity. AOGCM is an atmosphere ocean coupled general circulation model. And ESM is an Earth System model. So these are the acronyms I'll be using. And one way to think about these models is that they come in many different forms, and you can think about them on these 3 axes. So on the Z axis here, which is this one, if my laser pointer appears, there we go. We have what's termed integration. And integration is essentially how many components the models include. Another way to think about this is how far along the anthropogenic emissions to climate change cause and effect chain do they run? So they start at emissions and end at sea level rise, or do they start at concentrations and end just at temperature change, for example? And what we see in general is that energy balance models or reduced complexity models, we'll see in a second, tend to have more components, or they go further along that chain than most other models. At the other end of the spectrum, we have AOGCM, so these atmosphere ocean general circulation models, and they tend to have slightly less integration, largely because they're so expensive to run. On the other 2 axes, we have the detailed description, so how detailed the description of each process is. And then on the y-axis here, we have the number of processes. And so we have this hierarchy where at one end we have the simplified models, so the EBMs and RCMs. And at the other end, we have the AOGCMs and ESMs. In the middle, we have the EMICs, so these intermediate complexity models. You'll often hear the term ESM, and ESMs are essentially a superset of AOGCMs. They add the land cycle, particularly the land carbon cycle, to AOGCMs. So they're quite a useful tool. And in this project, I really refer to RCMs rather than EBMs. So RCMs, reduced complexity climate models, tend to cover what I'm actually looking at a bit more widely. EBMs is a bit more narrow than what I'll cover today. So really, this is where my project sits. It sits down this end of the climate model hierarchy, really on the simplified end, but with much wider integration than most models. So for just a bit of extra context, Earth system models look like this if you put them in a schematic. And the idea is that they cut the Earth into a number of grids. Each grid has some horizontal and vertical extent, and those grids exchange momentum, energy, carbon flux, etc. And running these models is really expensive because every single grid box has to exchange information with all of its neighbors, and you'll have millions of grid boxes. So on each time step, you've got millions, maybe billions of exchanges once you do all the combinations. And just keeping track of that many numbers becomes really computationally expensive. EMICs look more or less the same from a conceptual point of view. They just use bigger grids, which makes their computation slightly cheaper. There are a few other tricks you can play with EMICs, but I'm not going to get into them today. But on the other hand, if you did a schematic for an RCM, it might look something like this. So the absolute simplest RCMs will just take anthropogenic emissions, which is on the left here, in its very simplified form, and they treat the Earth as a single homogeneous blob, essentially. So they don't have grid boxes interacting, they just have one box, which is how they model the Earth. This is obviously a highly simplified view of the world, but it is very useful in many contexts, as we'll see today. If you do it a bit more detailed and a bit more properly, then you get a schematic which looks like this. This is Malta's schematic of how magic looks when you break it down. So we can see here that it actually splits the world into northern and southern hemispheres, and then into land and ocean separately. And the ocean has multiple layers, and those layers exchange heat, and they exchange heat, and that's how we kind of solve the Earth's energy balance. Now, RCMs typically focus on global mean quantities, and the fact that they don't have this gridded representation means they're much, much cheaper to run. When we actually look at the numbers, the difference is pretty startling. So in the top left here, ESMs, to do a single simulated year, requires thousands of CPU hours. So it's basically your personal laptop times about 200, and you run that for an hour, and that'll get you a single simulated year. In contrast, the RCMs take about 1/1,000,000th of an hour to run a single simulated year. And we translate that into how long it takes to do a scenario experiment. ESMs are doing taking months on a supercomputer with about 10,000 cores, whereas an RCM will take 1/10 of a second or so. So there's multiple orders of magnitude different here in their run times, and there's also completely different orders of magnitude in terms of computing expertise required, computing power, and computing cost. What you can see pretty quickly is if you want to analyze thousands of scenarios, not just a single scenario, thousands of months isn't going to work. If we're going to wait thousands of months, we may as well just let the Earth do its thing, and we'll find out what happens when we find out. It's really only RCMs which are computationally fast enough in order to do analysis of thousands of scenarios. And that's basically the crux of why magic appears at the heart of that SR 1.5 statement. For the timescales that SR 1.5 had for its analysis, only magic could do all the runs in sufficiently fast amount of time. So putting those two ideas together, so one, what we have from SR 1.5 and the research gap we had, and two, that reduced complexity models are kind of a key part of the tool, we end up with essentially this project's two overarching motivations. So one is that reduced complexity model evaluation is lacking, and the second is that reduced complexity models are widely used, and they're a key part of scenario categorization. Now, I could have done a project just on evaluation, but my supervisors encouraged me to go slightly beyond that and to think slightly bigger. And so what I've ended up with is how I think of reduced complexity climate modeling, which is essentially this diagram. So you have three modes which people move between. So an obvious one is evaluation of the models. The second one is development of the models. And the third one is applying the models to questions of interest. And we have the double-headed arrows here because you can go from any of these modes to any one other mode. You don't have to go around in a circle in any particular order. And people will do different parts at different times, depending on their expertise and interest. Now, this diagram pretty much frames my project in terms of how it ends up being structured. And just for completeness, if we put the project's goals actually into two specific goals, or the project's motivation to two specific goals, we'd have these two goals. So the first is to improve our evaluation of reduced complexity climate models. And the second is to identify key areas for improvement in reduced complexity climate modeling by exploring all three steps in this development, evaluation, application cycle, which we've ended up with. So if we return to our outline, we can see how these different chapters actually break down to the different modes I've just spoken about. So to start with, part of chapter 3 and chapter 4 and 7, or that's how it works, I think, in the thesis, focus on model evaluation. Then chapter 5 focus on model application, and part of chapter 3 and chapter 6 focus on model development. So as I go through the chapters today, hopefully you'll see A, how I'm moving through this cycle, and B, how the different bits connect together. So I'm going to start off with this chapter on data processing, in particular CMIP data processing. So quick bit of background, CMIP data is the data which comes out of ESM, so Earth system models. It's extremely complicated, it's large data, so I think the total data volume for CMIP 6 is about 16 petabytes from memory. So not the kind of thing you can handle without real expertise. And in general, getting hold of this data and using this data can be a pain. So what we've developed is a new software tool for handling CMIP data. And we've ended up producing a new set of CMIP-derived time series, and we focused on those which are relevant to reduce complexity modeling. So particularly surface variables, and particularly regional aggregates, so global means, hemispheric means, land and ocean means. And we use these time series in the following chapters. This wasn't an easy feat, but it's a relatively small part of the thesis, but it hasn't enabled a lot of the research which follows. So for example, if you wanted to compare the RCP projections from CMIP 5, the previous generation of CMIP, to the SSP projections from CMIP 6, you could download all the data, crunch it yourself, and then make a plot. Or you could just go to cmip6.science.unimeld.edu, and we've got all the data sitting there. You can make some very basic plots, like the one I've got in front of you, which doesn't show you a heap, it shows you a little bit, and then all the data is free to download and then use in analysis. I actually did a talk on this more specifically, and so the full talk is at the link you can see below. So that was the kind of CMIP data processing, which provides output for what comes next. If we move on, then the next part of the thesis was looking at how global mean temperature response from different RCMs compare. And so to do this, we kind of asked ourselves a pretty basic question, right? So how do global mean temperature responses from different reduced complexity climate models actually compare? Now this seems easy in principle, but at the time we asked this question, there was no central coordination for RCM. So there was no obvious way to get different modeling groups together to all run the same experiment and then to see how the different models compared. So what we did was we created this thing which we call the Reduced Complexity Model Intercomparison Project, or RCMIP. And the idea behind RCMIP was to follow the lead of the Coupled Model Intercomparison Project, a CMIP, so this project which focuses on the ESMs, the really complex models, and to do more or less the same thing, but for RCMs, so the reduced complexity models. So we wanted to bring the systematic routine intercomparison and evaluation that CMIP applies to their models to RCMs. There's a few steps involved in doing this. So one is that you need to have standardized formats, both for inputs and outputs. And that makes sure that everyone runs the same experiment. And then when you're doing analysis, you get it all back in the same format. You don't have to deal with a custom format from every model, because then it becomes impossible to do anything. You need to have standardized experiments. So everyone needs to run the same things as a sort of benchmarking. And then you need to get multiple research groups to agree and work towards the same timeline. And so it's in large part a community building exercise. We've got more details at rcmip.org, but what I'm going to show here is just quickly run through what we concluded. I unfortunately don't have time to go through all the details, but once we've done this, we can actually answer this question. And as it turns out, that once you compare reduced complexity models observations, they all will look fairly similar, and part of that is because they're so easy to tune, so they all do a pretty good job at getting more or less through the middle of observations. One of the things we discovered was that there's actually ongoing challenges for emulating more complex models. So if you're just trying to reproduce the response of a more complex model with a simplified model, it's actually not that simple. And especially when you move to scenarios, so away from kind of idealized experiments into more scenario experiments where you've got multiple climate forces, natural forces, and climate feedbacks, things get much more complicated. And so we found that the job which emulators are currently doing isn't as good as we thought it was, and there's some clear areas for doing better. Beyond what we achieved in a kind of scientific sense, we actually achieved quite a lot from a community sense. So we actually established this community, and we had 14 groups, ran tens of experiments. All the analysis worked pretty much without a hitch. It's all openly available at that website if you want to go and have a look. We managed to get, I think we ended up with something around 26 co-authors to write a joint paper. And the most important part really was that getting RCMIP phase 1 set up meant we could then go and run the same thing again without the pain of defining all our formats. So we could actually do further exercises. The key one of that is RCMIP phase 2, which I'll come back to at the end of this talk. Unfortunately, that's all I have time to talk about in terms of RCMIP phase 1, but I'm going to move on now to how we applied an RCM to the question of the remaining carbon budget. So up until now, I've obviously skimmed through a lot of the details. Here, I'm actually going to dive into the detail much more. So I haven't actually done a talk on this particular piece of work yet. It's something I'm hoping to do in the future. But here we'll try and slow it down and actually look at how some of the research was done, what some of the results were, and how it all works in a bit more detail than I've had time for up until now. So we want to look at the remaining carbon budget. And the question we had was, well, SR 1.5 introduced a new, highly idealized, what I refer to as segmented framework for assessing the remaining carbon budget. And the question we had was, do the simplifications made by SR 1.5 introduce any unexpected bias? So to start with this, we're going to have to talk about what this SR 1.5 framework actually is. So the first step in it is to define what you mean by your remaining CO2 induced warming before you hit net zero CO2 emissions. So that's this delta T term here on the left. Now, SR 1.5 treats this term as the sum of 4 terms. So the first is your warming limit. So you might say, I want to have a peak warming of 1.5, or I want to have a peak warming of 2 degrees, or 1.8, or whatever else. Then from this, you remove the historical warming. So that's the warming observed up until today. It's roughly 1.1 degrees. Next, you need to take out all the non-CO2 contributions. And that's a bit complicated to calculate, but in this framework, it's just a single number. And then the final step is you reduce any warming which happens after we reach net zero. Now, current best evidence is that this term is actually 0, but it's included here just for completeness. So when you put all this together, you end up with how much more warming can be induced by CO2 alone before we get to net zero. Then what you want to do is convert this CO2 warming into a total amount of CO2 emissions from here until net zero, or from here forever forward. Obviously, once you reach net zero, you're not emitting anymore, so the total CO2 emissions stop rising. And the SR 1.5 assumption was that you could do that conversion with this single parameter in this single equation. And this parameter here is called the TCRE, the transient climate response to emissions. And it quantifies per unit of CO2 which you emit, how much warming do you get? So we use this equation to determine C. And then finally, our remaining carbon budget is these CO2 emissions, but then we have to subtract any other correction we want to include for processes we haven't included elsewhere. And so the example in SR 1.5 was permafrost. The assessment was made that permafrost wasn't in any of the previous terms, so they need an extra correction term to account for the impact of permafrost. When you put it all together, it looks like this. So it's not too intimidating, but there is quite a lot going on. Now, there are a couple of assumptions in this segmented framework. So the first is that all the warming contributions are independent. So what that means is that here, all these terms are considered separate. There's no feedback terms anywhere. So one of the things we know, for example, is that the carbon cycle responds to non-CO2 climate forces. So we know in the real world, there actually should be a term, something like CO2 induced warming as a result of feedbacks from non-CO2 climate forces. There's no such term in here. So there's clearly an approximation going on. And that's one of the key assumptions of this SR 1.5 framework. It simplifies things, but there is a question of how much that approximation matters. The second assumption is that CO2-induced warming is linearly related to cumulative CO2 emissions. And that's this equation. So here, warming is linear with, this term C, this cumulative CO2 emissions. Now, we know that's an approximation. We've known that's an approximation for quite some time. And so our question was, well, to what extent is this approximation a problem? So what we do here is we've actually proposed a way to account for nonlinearities between this delta t and this C term. And the way we do that is with this updated equation here. So the one on top, this is what SR 1.5 used, and the one down below is what we did in our research. So instead of having this linear relationship, we actually use a logarithmic relationship, which is this log here. So now the warming scales logarithmically with cumulative CO2 emissions. And then we have some other parameters. So this gamma parameter here, the scaling parameter. This delta T 2 times is the warming when atmospheric CO2 concentrations double in what's referred to as the 1% CO2 experiment. And we'll see why that matters in a second. Then we've got cumulative carbon emissions. This parameter here is, I call the nonlinearity parameter, alpha. We'll see again why in a second. And this final term is the cumulative CO2 emissions, again, at the point at which atmospheric concentrations double in the 1% CO2 experiment. The 1% CO2 experiment is an experiment at which atmospheric CO2 concentrations rise at 1% per year. Now, one of the key properties of this update is that if you take the limit where alpha goes to infinity, the equation reduces to this. So all the logs drop out and you end up with a linear relationship again between warming and cumulative CO2 emissions. And by using these two terms which we defined earlier, it actually returns to exactly what SR 1.5 used, because the TCRE is defined as the ratio between warming at this doubling of CO2 point and the cumulative carbon emissions at this doubling of CO2 point. So that nice property of our update is that you can actually clearly relate it to existing methods. So rather than making it impossible to tell how our update relates to existing research, it actually gives a very clear relationship between the two. Now, the useful thing here is that we can then go through and look at, okay, how big is alpha? So how big is this nonlinearity parameter, or how small, more to the point, because the smaller alpha is the more nonlinear. Or for example, what is gamma? How much do we need to scale away from the typical TCRE we would get? There's a gamma missing here for those of you with keen eyes. So what we did is we used an RCM, we used Magic 6, and we used it in multiple calibrations to actually perform simulations without the segmentation. So that's one part of the process, and two, to determine the size of the nonlinearities. And we end up with this figure. So in blue here is the model simulations. So they're simulations which A, include the interaction terms between components, and B, include nonlinearities. The red here is the SR 1.5 style of doing things. So you don't have the interactions and you don't have the nonlinearity. And this cyan blue curve in the middle is what we propose as our update. So you still don't have the interaction terms, but you do have the nonlinearity. And what you can see here is that really the thing that matters is including the nonlinearity between CO2 induced warming and cumulative CO2 emissions. That almost completely closes the gap. The fact that the SR 1.5 setup actually assumes independence between the terms seems to not matter as much as we initially thought it would. And that's kind of summarizing these conclusions. So if you consider the nonlinearities, you get around a 10% improvement between this segmented framework and model simulations, which actually include all the required bits. Or put another way, if you don't include this nonlinearity, then you're underestimating the budget by about 10%. And second, you can actually resolve the difference between the two. And it's the segmentation is not such an issue, although that assumption is actually a little bit sensitive to carbon cycle and climate response in the particular calibration we use. So there's two key implications. One is that you might want to tweak the remaining carbon budgets are assessed, although this 10% number is actually well within many other much larger uncertainties. So it really is a tweak rather than rewriting the book. And the second is that there are clear areas for improvement in RCMs. And so one of the things that you learn from actually applying RCMs is where you think you can make them better. And so to us, it was pretty clear that there were some issues with using magic, which we want to improve. And the second was that it would have been great to have carbon and climate calibrations to CMIP 6. We actually didn't have those, and so we had to use older ones based on previous generations of CMIP, and they tempered our conclusions somewhat. So that's kind of our application chapter, and goes through how I've applied a reduced complexity model in this thesis and how the kind of lessons I learned. So next bit I'm going to come to is some of the development work I did with Magic 7. And what I did was help develop Magic 7's new probabilistic distribution. So probabilistic distributions go beyond best estimates. So rather than saying we think that we'll have warming of 2.3 degrees in 2100 under scenario X, they actually allow us to make statements like, under this emissions pathway, the likelihood of staying below, here I've got 1.5 degrees, is 63%. You can only make those sort of statements if you have some confidence in, if you have A, probabilistic distributions, and B, some confidence they are representing our uncertainties well. So what I've done is update existing methodologies. So we've extended the work done by Malta in 2009, and that's updated handling of observations, particularly their uncertainties, and we added this subsampling step in multiple dimensions. So I'm not going to talk about the observations in any detail today because the uncertainty gets into a whole bunch of maths I don't want to touch, but I want to talk about the subsampling just very briefly. Now, the subsampling, the idea is that we go through, and with our model, we determine model parameters which are consistent with our understanding of the climate system. And one of those parameters we might choose would be, for example, the climate sensitivity. And from our model, we get a certain range. But for some applications, we actually don't want to use our model range. We want our model range to reflect some other independent assessment. So for example, the climate sensitivity ranges assessed by the IPCC. This isn't actually a new idea. The same thing was done by Malta in 2009, and then Yuri Rogli, and Malta was a part of this team in 2012. But what we want to do here is, rather than just subsampling in one dimension, and the typical dimension was climate sensitivity, we want to subsample in multiple dimensions. And the idea is that we want to meet the independent assessment in each dimension whilst also keeping the covariance between the dimensions that we've found from running our multiple times. And the idea is that you end up with a distribution which not only captures the independent assessments, but also adds covariance information between these assessments based on the model structure. And the way it looks, if you do it in practice, is that you might have some assessed range, which is what we have up here, and this might be what comes out of your model. And so what we do is we subsample this distribution to get what's shown here, which is much closer to the assessed range. And we don't do this in one dimension, but we'll do it in multiple, and we'll end up with a new distribution, which reflects not only the independent assessments, but all the variance between them. And that's kind of the key step that's been done in this chapter. Alongside that, we've also implemented the entire pipeline in Python, and we've made it completely reproducible. And the idea here is that we want to rerun the entire pipeline in future with different input assumptions to examine the impact. And there's a lot of assumptions that have to be made in this process, so there's a lot of things that we can test in the future. We derived a probabilistic distribution, which we're going to use in RCMIP phase 2, which is the next part of the talk. And we've also separately derived a new probabilistic distribution, which is available for the authors of the IPCC 6th assessment report. So that's been quite a key part of the process. So, final part, and I'll wrap up. The question is, how well can or do probabilistic distributions from different reduced complexity climate models capture assessed ranges? Now, the idea here is that often when, so let's just come back to the start of the talk. So the SR 1.5 made this comment about being unsure of the veracity of reduced complexity climate models, and especially when they're assessing emissions pathways. The idea here is that after all the work I've done in the previous chapters, we actually want to fill that knowledge gap. And that's what this chapter is purely focused on. So what we want to do is say, okay, in the IPCC process, typically what we have is assessed ranges for a whole bunch of metrics. They all come from different chapters and they're all more or less independent. How well can we get any given reduced complexity climate model to actually match all these independent assessments simultaneously. And if we can assess that and quantify that, then we won't have this knowledge gap anymore. We'll actually have a very good understanding of the extent to which these models are biased in one way or the other, where they perform well or where they don't perform quite as well. So that's the question we're asking here. We're introducing a methodology to actually do that. So what we do is we take all these assessed ranges, and in this case, we use proxy assessed ranges. So the 6th assessment report isn't available yet. The 5th assessment report has been updated by new literature. So we take different assessed ranges from the literature. So we get things like an assessed range for historical warming, an assessed range for climate sensitivity, transient climate response, et cetera, et cetera. And the key here is that we can't just have a best estimate. We need a best estimate and the range of estimates. And we're going to use those ranges, and we're going to compare our reduced complexity models to them. So for example, we had, I think it's 10 models participate in RCMIP phase 2, and we asked them all to submit these probabilistic distributions. And for each of those metrics, every model will have its own range. So what we can do is we can compare our proxy assessment, which is this black bar here, to each of the model ranges. And we'll see that some models do a particularly good job and are pretty close to the assessment. So I think Magic 7 here, and then Citzer OCM also does quite a nice job. Other models might get the central assessment right, but they might be too high at the top end. So for example, the FAIR model in here, whereas other models might be skewed in one way or another. So MCE appears to have too low equilibrium climate sensitivity in general from what we've got so far. And we do this over all the metrics, and we get these summary tables. And the summary tables allow us to answer the question which NSR 1.5 felt they couldn't, i.e. you can quickly see where the models had issues. So for example, FAIR has quite a strong bias in the TCR, especially the low end. It's far too high. Similar with Hector, and actually similar with Magic. It's something we found across quite a few of the models. Whereas Magic does a very nice job of getting the CO2 range, CO2 effective radiative forcing range right. And so you can go through and you can actually answer this question, which SR15 didn't feel they could. So I'm not going to go through all the results today, but one of the key results is that, and this is kind of obvious, but it's important for the use case we're considering, that if the models which use the assessed ranges in their constraining match the assessed ranges better. So the temptation is often to just pull an existing probabilistic distribution off the shelf. But what we found is if you do that, you're often going to have strong biases between the assessment you're trying to reproduce and the distribution you're actually using. And the second one is that the best performing distributions actually match the assessed ranges fairly well across the majority of metrics. And that's kind of surprising because all the assessments are independent. So there's no reason for them to be consistent, nor for a model to be able to actually reproduce them all. So that was quite good news, especially for the scenario categorization community. One thing I have to stress is that we're actually assessing distributions. You're not assessing the models by themselves because their behavior really varies depending on their parameter values. You're assessing the distributions and the parameter distributions. And that's quite different from, example, the CMIP model assessment. Because the CMIP models are so complicated, they tend not to have this parameter, perturbed parameter setup like we've got here. So what we've ended up with is a really nice way of assessing probabilistic distributions, and it allows immediate identification of model biases. And we've actually got all the software in place to handle the data required to do this. And it's about 2 orders of magnitude more data, which you have to handle to do this sort of stuff than if you're just doing best estimate assessment. And it's nice to know, as I said, that some of these distributions are remarkably close to the assessment across a range of metrics. So it looks unlikely that the tools we've been using have major flaws, which is reassuring given some of the statements which are made based upon their outputs. So concluding and looking at what could come next. So what could come next? A clear one is new emulation setups, as we saw both in the application chapter and also in RCMIP phase 1. Emulation is a clear area where there's work to be done. We've got further phases of RCMIP, which we would like to do. So one is actually unifying some of the assumptions which are made across models before we make the comparisons. And that makes it slightly easier to compare apples with apples rather than apples with oranges. We want to delve into the carbon cycle, and we want to delve into some more detailed analysis of the specific components of models. And one big one is the aerosol effective radiative forcing. So there's some big questions there about what the best way to represent it actually are. On the application side, we've got a whole bunch of IAM scenarios coming out soon, which we need to go and assess, and we want to see what they tell us about the transition required to meet goals like the Paris Agreement. And if you look at the broader picture of reduced complexity modeling in general, it's pretty clear there's improvements in reproducibility, openness, and ease of use to be made. And that doing all of those would actually benefit both the developers, but also people who are trying to assess the models and people who are trying to use the models. I think there's some really key steps to be made. So just to wrap up the conclusions, we obviously made a new CMIP-derived data source. There are clear areas for improvement in emulation. We worked out a way to include non-linearities in remaining carbon budget assessment, derived new probabilistic distribution or distributions for Magic 7, and we found that the best performing RCMs can simultaneously capture a range of assessed ranges. So putting it all together, returning to this statement from SR 1.5, so the veracity of these reduced complexity client models is a substantial knowledge gap in the overall assessment of pathways and their temperature thresholds. And in my opinion, and hopefully you'll agree, I think this gap is now much, much smaller. With that, thank you all for your attention, and I'll hand back to Malta.
Thank you so much, Zebedee, for that fantastic tour de table, and thank you also for putting up this slide, which is a reminder of good old times, smiley faces in the Climate and Energy College. So we have now an open Q&A session, and given that it's a completion seminar, afterwards the panelists who you see here online, also David Cavoli, Alexander Knowles, and Robin Schofield and Peter Rayner are retweeting and quizzing the candidate a little bit further in private. But first of all, question is open to the floor. Whoever has a question, please ask it either in the chat or in the Q&A, and I will ask you to unmute yourself. So the first question is from Robert Edmonds. I just unmute your microphone, and then you can, now you should be able to talk.
Look, this is an interesting field, but I attended a lecture with David Carrolley over at La Trobe, I think it was early last year, which was very interesting on the topic of climate change. So I was sort of follow up on this. But, you know, with El Nino and El Nina, those, I don't know how good the models are at seeing the switch when one comes in and the other one flows out, because they're pretty hard to predict themselves, aren't they? The weather changes, the cycles there. Anyway, it's probably a stupid question, but I'm just wondering about how that works.
No, not a stupid question at all. Thank you, Robert. And David will be thankful that you've brought this up as well, because we've had a few discussions about this in the last few weeks. So the short answer is that RCMs in general don't have any representation of El Nino and La Nina. So what they focus on is global mean quantities, so global mean temperatures in particular, and they tend to focus on annual timescales, and sometimes much longer than annual timescales. So at those sort of timescales, you obviously don't resolve El Nino and La Nina properly. And what's more, because RCMs only have a single box typically, or maybe 4 boxes, they don't have any of the dynamics required to produce El Nino and La Nina type representations. So let me just flick back through my slides quickly, and I'll just show how this works in the model hierarchy. So essentially the way that manifests here is that on the detailed description axis and in the processes axis, RCMs are too low to actually have El Nino and La Nina. And that's obviously a key feature of them, because you need some way of doing that if you want to do, for example, near-term projections. And that's why we tend to think of the climate model hierarchy as a hierarchy. RCMs by themselves can't answer all the questions of interest. They can answer a specific subset, but you have to have the other models in the hierarchy to answer questions like the one you're pointing to with respects to El Nino and La Nina. And I'll just give a plug here for one of my former Climate and Energy College colleagues, Mandy Freund, who has done a lot of work on this. And if you want to get more information on that, I encourage you to look up her work.
Thank you. And the next question is from Gemina Jeffrey. Gemina, you should be able to unmute yourself. Yes.
Yeah, so I was just wondering why you want to have more scenarios. So you said that one of the important things about RCMs is that you can run lots and lots and lots of scenarios really quickly. why does it matter that you need all those different scenarios? Why can't you just have a less emissions, more emissions, and then interpolate between those?
This is a very good question. So there's a couple of reasons. One is that when we're looking at future emissions choices, there's quite a few knobs we can turn. So we've obviously got CO2 as the big emissions driver, but there's all the non-CO2 emissions. So for example, methane, nitrous oxide, HFCs, CFCs, plus all the aerosol precursors. And you can end up with some slightly complicated couplings between them. So in general, CO2 emissions from fossil fuel generation, particularly coal, comes co-emitted with sulfur dioxide emissions. So modelling teams around the world spend quite a lot of time thinking about this, and not our modelling teams, I should point out. These are generally integrated assessment models. We'll think about what are all the plausible ways that these knobs could be turned, or how can we change our emissions? And then the question is, well, you've actually got, you could have a high CO2 scenario with low methane, or a low CO2 with high methane. And you want to know how much those two different options actually trade off against each other. So simple interpolation won't actually get you the answer. You have to go much, much more detailed, and you want to look at lots of scenarios to try and get a sense of A, how much these things can trade off, but B, in some sense, how linear the trade-offs are. So if you go, high CO2, low methane, is it the same as medium CO2, medium methane, and low CO2, high methane, or is there some other extra dynamics going on in there? And you can imagine that you combine all of these different options, and very quickly you go from high emissions, low emissions to hundreds and thousands of different combinations once you've gone across roughly 40 different greenhouse gases and 7 aerosol precursor species. Hope that answers the question.
So you can't combine the greenhouse gases as this isn't the forcing number, you have to treat them individually. Is that correct?
If you're going to start with emissions and work forward, then yeah, you have to treat them all differently because they have quite different properties. Methane is what's termed short-lived, so it has an atmospheric lifetime of about 10 years, whereas CO2 is what's termed long-lived, so it will have a presence in the atmosphere basically forever once we emit it.
Okay.
So you have to treat them very differently.
Thank you, Jamina. And now we have the next question from Neil Marshman.
Zebedee, great work, well done. Yeah, I learned a lot. I can't say I understand it all, but I learned a lot. My question is, how does the accuracy and precision of these models deteriorate, I suppose, as you move from 1.5 degree type of modelling to 2 degrees, and I suppose we may have to do some beyond 2 degrees. So does it drop off significantly that would affect policy decision making or not?
Yeah, thanks for the question, Neil. I think there's a tricky part of your question, which is you ask me how accurate they are as we go from 1.5 and 2 and beyond. And the issue here is we don't really know. And the reason is that we don't have a world where we've had 2 degrees temperature change in 150 years. So we kind of don't have any real validation data. I can rephrase the question to how confident are we in these models' responses as we go from 1.5, 2 degrees and beyond? And I think we're certainly more confident in their responses at the lower end. At the higher end, things become tricky, and they become tricky largely on this processes axis. And the issue really is, well, at these higher warming levels, are there processes, A, which either aren't in our models, or B, which are underrepresented in our models, which can lead to feedbacks we haven't thought about? And this is where you hear about the term runaway. And the idea is that there are some processes which we either don't have in our models properly, or we don't understand properly, which actually, once we get beyond 2 degrees or so, will start to trigger each other, and actually we'll get what they term runaway warming. So rather than the warming being controlled by human emissions anymore, it will now be controlled by the processes within the Earth system and will be completely beyond our control. So I think we're certainly a lot more comfortable in our conclusions at the low end of warming, and as we get much beyond 2 degrees, we're starting to become increasingly nervous that there's something in the system we haven't thought about and we're not representing. Hopefully that is a suitable answer.
And we have one more question from, sorry, Neil, you wanted to?
No, thanks for that.
Okay. We have one more question from the floor from Sonia, and then we go over to the tricky questions, which come from the panelists like David Cavoli, Alexander Knowles, Robin, and Peter. So Sonia, you have the floor.
Thank you, and congratulations, Zeb, on this big milestone. That's a great talk. So my question relates to aerosols, as you could have guessed. The AOGCMs and ACMs are becoming more and more complex and are starting to consider aerosols more seriously, but we also know that they have a lot of problems. And you mentioned that the RCMs have a few big questions surrounding them. So I'm just wondering, what are these big questions, if you can put them simply? And do you foresee any problems in sort of when you do emulate the more complex models that have their own problems with regards to aerosol forcings, and then back to a different model with its own problems? Do you see more problems, I suppose?
Thank you, Sonia. I'm just making sure I've got that all written down. So at this point, I just wanted to point out that my confirmation, it's not my completion, my confirmation seminar's title was actually Improving Aerosol Representation in Reduced Complexity Models. So this one, I should probably apologize to Robin because I didn't end up doing that. And I think that was pretty much the premise of her coming onto my advisory panel. So I'm sorry that I changed tack, but there we are. But I think I do have enough knowledge to answer this question. So one of the big questions for reduced complexity models, and this is one of the things we discovered in RCMIP phase 2, was that there's increasing amounts of research coming out suggesting that there's actually quite a strong temperature feedback onto aerosol effective radiative forcing, and the mechanisms are not completely across, but I think they're related to do with natural background emissions. And most RCMs don't actually include any sort of temperature feedback in that parameterization. There are a couple that do, and the difference between the models which do include it and the models which don't is enough that their likely ranges almost don't overlap. So it's a pretty serious question in there. And it's quite unclear to me which one's correct. I think it's quite unclear to the community which one's correct. And so there's quite a big uncertainty floating around in that particular realm. And that's started to come out through these more targeted AOGCM experiments, but also new developments. So that's kind of where I think what next and what seems to be coming out of the developments. With regards to the flow-on effects, obviously the problem with all of this and some of the biases in AOGCMs is that if the AOGCMs are biased and then you get your emulated and match the AOGCMs, then you're just propagating a bias forward. So we try where we can to also use observational constraints. It's tricky, and it's extremely tricky when you're looking at temperature feedbacks because we often don't have enough warming in the past to really get a sense of how big they might be. So I think that's going to be a really interesting area for research over the coming years, and one that I hope to get to. Peter Rayner, another of my supervisors, said to me once that the best PhD projects start out as PhD projects and end up being your first postdoc. So that's what we'll see happening here. But yeah, I think the other thing to be said is that there's a question, and again, a question I wanted to answer but didn't in my PhD project, about actually what's the minimum number of spatial boxes you need in order to have a defensible representation of AOGCM aerosol responses. So MAGIC has 4 boxes, and that obviously helps. There's quite a few models which just run around with 1. And the question is, if you use a single box model compared to a 4-box model, how much realism or emulation ability are you trading off? And is there a point at which you actually can't, the loss of spatial resolution really starts to hurt? And that's not a question I answered, but I think it's a really interesting one for the future.
Thank you so much, Zebedee. And now we go to the next phase of the completion seminar, which is public questions by the panelists. And so now, panelists, just unmute yourself and start asking questions. The first one is David Cavoli, but then just come in. And then afterwards, we conclude this webinar and go into a closed session. So thank you, David.
Thanks, Malte. And Zeb, thanks for a really nice synthesis of 3.5 years of work. And I've actually got a question that I think directly follows on from Sonia Fitter's question as well. And that is, you talked about in your seminar the advantage that RCMs have in being able to look at lots of different scenarios for different greenhouse gas emissions or radiative forcing scenarios and things like that. Have you thought much about using RCMs to assess possible geoengineering scenarios, either in terms of solar radiation management scenarios through aerosol injection or carbon dioxide removal scenarios through artificial means, whether they're vacuum cleaners that suck up carbon dioxide that aren't trees, or artificial trees that capture carbon dioxide? Can those sorts of scenarios be assessed by RCMs better than, for instance, coupled ocean atmosphere models?
Thanks, David. Now, there's a term I'm not meant to use in here somewhere. I think it's geoengineering. I think Malta likes to make the distinction between solar radiation management and carbon dioxide removal. Malta, you can correct me if I've got this backwards somehow. So I'll start with carbon dioxide removal because that's the easier one. I think on that front, there's quite a lot of questions about how the carbon cycle would actually respond to large-scale carbon dioxide removal. The bad news is that I, off the top of my head, think that uncertainty is likely to persist for a couple of years. The good news is that we recently had a project funded in order to answer more or less specifically this question and to try and improve the representation of the carbon cycle in MAGIC, which I'll be working on starting in the middle of this year is the plan. And so hopefully we'll have much better answers and a much stronger understanding in a few years' time. But I think the idea there is that you want to couple your integrated assessment model with a reduced complexity model, and you have to use a reduced complexity model because only it's cheap enough to actually do that coupling. So I think there's some really good lessons that we learned from the ESMs, and then we need to get them into RCMs as best we can, and then actually let that information propagate beyond the physical science realm into the socioeconomic realm and start to see the feedbacks between the two. For solar radiation management, I think you can do idealized experiments really nicely at the moment, and they'll give you quick indications of how things might work and stuff like rebound. If you get a program up and then you lose funding for it and it all shuts down, what might happen? Would you end up back where you started, somewhere worse? If you wanted to get into the nitty-gritty details, it would really depend, I think, on a careful analysis of what we think is going to happen with any proposed technique. And obviously some techniques would have extremely localized impacts. So there we'd really have to dig into, again, the questions I was talking about with Sonia about spatial resolution and the importance of different levels of spatial resolution versus, atmospheric heights of injection and these sorts of things. And I think depending on exactly what technique's being proposed, there are some really big questions about the degree to which RCMs could actually capture the required responses and the required dynamics. So I would be nervous about making accurate statements about using an RCM for solar radiation management, but comfortable making broad statements about loose dynamics.
Any questions from other panelists?
Am I unmuted?
Yes, we can hear you, Peter.
Great, yep. I was interested in going back to the kind of comment on the ranges and the fitting the multiple assessed metrics. And I wonder if you could make a comment on whether you think that the current generation of RCMs are at about the right level of complexity. So given the range of things we have to match, let's put in a straw person here, that RCMs are more complicated than they need to be. That when you actually look at the kind of emerging constraints across the range of things we have to fit, you actually don't need as many knobs to fit the available evidence as RCMs actually have. Do you have a sense of whether we've got this complexity balance about right?
I think in some areas it is about right. In other areas, it's not quite there. So in the temperature response to radiative forcing, which is kind of typically referred to as the climate component, I think the complexity range is about right. We've got a range of models which go from single layer oceans through to MAGIC's kind of 100, 150 layer ocean, or even more if you want to spend the computing power. And I think those responses pretty well match what we think they should. And the key really seems to be how you represent what gets called in various ways kind of effective climate feedback. You need to have some way of making that state dependent, but as soon as you have that state dependence, it seems like you can reproduce the results from more complex models fairly well. The more interesting point is the carbon cycle. And there I think we're actually probably, well, there are some models which I think are over complex and others which are under complex. And we haven't quite worked out what the balance is there yet. And it's not that easy a question to answer because the carbon cycle dynamics is so much more complicated and because the uncertainty, especially in land carbon cycle uptake, is so much larger. So I think in the kind of, the climate space and then also the kind of non-CO2 greenhouse gas cycles where complex enough and the complexity is about right, there's really the carbon cycle where it's a very open question. And I think at one end, simple impulse responses are too simple. At the other end, there's a model called Oscar, which requires you to have basically land use maps on a quite detailed regional level just to run it. I think that's too complicated and we're somewhere in the middle. Magic's trying to get there, but it's, again, got a few bits and pieces we need to iron out in order to really settle it down.
Sure, good.
Any more questions from the panelists?
Robin, do you want to go first?
Sure. It could be a quick answer. The water feed, so you talked about having no feedbacks on the temperature. How's water dealt with? Like, can the enhancement of, like that the positive water feedback on the temperature?
The stratospheric,
it's just, sorry, it's just more that, a warm atmosphere can hold more water, therefore you'll get more warming.
Okay, yeah, the water vapor feedback, as it's also known. That tends to get wrapped into our, I believe, climate sensitivity parameter. I'm going to look at Malta and hope that he nods here. So basically what it means is that it's not explicitly in there, or you could kind of tease it apart, but it's wrapped up in a single number which incorporates a whole bunch of different feedbacks. You could make it more explicit, but yeah, so it's in there. It's not as simple as just this is the exact number that's being used. But we tend to sample such a wide range of climate sensitivity in general that will cover pretty much the entire plausible spectrum.
Do you think it would be possible, Mike, or I guess I'm asking, how easy is it to take that out? Because that would be a step on the way, perhaps, to aerosols, and it's behaves a little differently.
I mean, again, depends how complicated you want to make it. In a very simple way, it'll be very easy to take out. If you wanted to do it in probably a way that's more faithful to the underlying dynamics, it would require a bit more thinking, I think, just because of the way that water vapor would then have to be tracked and used in various parts of this model.
The way forward would be to express, rather than the climate sensitivity that goes in, that we transform into a single lambda feedback factor, which is the inverse, to express that lambda as a sum of the Planck lambda, the lapse rate, the cloud, the water vapor, etc., and then assume ranges for each of those, and then do the probabilistic constraining so that we get the cross correlations right, because if you're at the one end of the one, then you can't be at the top end of the other. So that would be the way forward there. Other questions, Alex?
Thanks, Malte. Congratulations, Zeb, on this very impressive summary of your work over the last years. So thanks for that. I just wanted to follow up on RCMIP a little bit, because that's also a real big step, I guess, for the community to compare for the first time very transparently the RCMs and what they actually do. So from this exercise, I guess you've learned a lot about the individual models, but also you've learned a lot probably about magic itself. So what would you, what's your sort of the most burning topic you would want to address from quality issues that you've maybe experienced during this exercise?
Thanks, Alex. I think carbon cycle is the clear next step for us. That's really the area where there's the most questions. It's the least clear. You need to dig into the models, and there's kind of the most disagreement amongst the models about what's going to happen in future. So I think that's the area that needs the most attention and will start to help us, especially for these emissions-driven scenarios that we're looking into the future, coming from IAMs. That's the area that will really help us get a sense of what the true uncertainties are and actually what could be hidden in the land carbon cycle in particular, because that could go very different directions. And I think we're doing an okay job of capturing the range at the moment, but we could definitely do much better, and we could have a much nicer representation of the underlying dynamics, or much nicer parameterizations.
Thanks.
Thank you so much. That concludes our public part of the completion seminar. Zebedee, fantastic job. We are now going into a closed session, and we are looking forward throughout the year to have you guests in our other seminars that are coming up. There's Peter, you're the master here. You can correct me if I'm wrong. At the moment, there's no one yet firmly scheduled, but yeah, watch out on our Climate Energy College newsletter space or the seminar webpage for more to come. It's going to be an exciting year for climate science and climate policy in general, and so stay with us and see you soon again. And for the panelists, I sent you by email another Zoom link. We see you there. Thank you. Bye-bye.
Thanks, everybody.